I'm going to talk about MemorySanitizer, which is a new tool that is developed at Google in our Moscow office. Our team has developed quite a few sanitizers up to date. There was AddressSanitizer that detects addressability issues, namely buffer overflows and use after free bugs. And there is ThreadSanitizer that detects data races. So this new tool detects a new kind of bugs, and this is what it detects: uses of uninitialized values. So in this example, we've got a stack array which is uninitialized, filled with garbage when you enter the function, and MSan, MemorySanitizer, reports that at this line we've got some code that depends on an uninitialized value. Note how it also reports the location, the name of exact variable where this uninitialized value was created. This is something that's very hard to do in a dynamic tool like Valgrind or DynamoRio, and very easy to do in a compiler tool. So how we do it? We maintain a shadow memory, which is one bit of shadow memory for each bit of application memory, with values of 1 when this bit is uninitialized and 0 when it is initialized. This is not very compact. Some other tools that do the same have more compact representation, but this way is faster. Because this is a one-to-one mapping, we have a very simple formula for calculating the address of shadow. We map a fixed location in memory at 0x2, a lot of zeros, and we force all application addresses into higher memory. There is a choice. There is always a choice between reporting each case when we've got a not fully initialized argument to some IR instruction, or propagating this uninitializedness to the result of that instruction. First of all, we cannot report every operation on uninitialized values as an error, because there is this very common case when you copy a struct with padding inside, with hole, and this hole here is typically filled with uninitialized data, and you have to allow at least copying of such data without warnings. So apparently it's also common to do some simple math on uninitialized data and then just throw away the result. It happens, and our tool allows it without warnings. We operate on IR, and we assign shadow temps to each application temp, and we instrument every IR operation by either propagating shadow to the result of this operation, or warning about the use of uninitialized value. We try to warn only when we cannot propagate any longer. For example, when PC, program counter, gets poisoned because of a conditional branch that depends on uninitialized value, or when this uninitialized value spills into environment. For example, as an argument of a system call. Here are some typical IR instructions and how we instrument them. For constant values, obviously have a clean shadow. For loads and stores, we load and store their shadow values from memory. And for example, shifts are very easy. If you shift an application value, we just add a similar shift for its shadow value. So the bits are just move. Logical bitwise AND is a bit more complex. This equation is exact, so it will. This is the shadow of the result, and this will calculate. This will have ones in place of bits that cannot be computed using only known unpoisoned bits of B and C. Something even more complex we do for equality comparison. So if B and C are partially poisoned, so partially unknown, we can, in some cases, we can still say that we know the result of comparison. For example, if there are two known bits that are different, and these formulas say exactly that. For vector types, we just use the same formulas. Luckily, they translate exactly. Some instructions have very complex semantics. For example, addition. It's not very easy to say which bits of the results of the addition results are defined, and if some of the arguments are not fully defined. We use this common propagation logic, which is bitwise OR. The alternative would be to report immediately if user application tries to add two values, one of which is not fully initialized, but it is actually much slower because we've got a branch and we have to evaluate a condition. So we just do bitwise OR of shadow values. This operation has some nice properties. It never makes a value less poisoned. It will not lose one bit at any position. And it will not make a poisoned value fully clean. So it kind of preserves the uninitializedness information. One tricky instruction is a relational comparison. One would think that it doesn't make sense to relationally compare two values when at least one of them is not fully initialized. But it turns out sometimes this is a valid operation too. For example, this case, if we have a bit field and we extract one field of it and we cast it to bool, there is something in inst combine that will turn that into a comparison. It will load the whole byte and it will check that it's higher than 7 in this case for 3 lower bits of that byte. Yeah, so this is like this. We've got A poisoned, its value is unknown, and we've got B fully known. And if we compare B greater than C, we know the result. It's either bigger or not, but it is clear. It is unpoisoned. So when that became clear, we attempted to implement shadow propagation through this instruction in an exact way. And here is how we try to do it. We know the result of comparison if taking into account all the poisoned bits of arguments. We know the range which may be occupied by the arguments. And if these two ranges intersect, then the result of comparison is unknown, and if they are distinct, then the result is known, initialized. Unfortunately, this turned out to be very slow. We've observed 50% performance degradation on one of the spec benchmarks. So we've had to make a compromise. We do this exact propagation when one of the arguments is a constant to accommodate this case, this one. And otherwise, we just propagate a shadow using bitwise OR. tracking origins. So one very important feature of MemorySanitizer is its ability to point the location where this uninitialized value was created. This is not the place where it was last loaded from memory, but rather where it first came into existence. For example, if you enter a function that has an array on the stack, that's when those bits in that array become uninitialized. To track that, we use a secondary shadow. We've got 4 byte origin ID for each 4 byte of application memory. We place it alongside the normal shadow, and it is obviously not exact. So if 4 bytes of application memory contain uninitialized values coming from different allocations, then we may report either of them. In fact, we will always report the one that was mixed in later, the latest. Propagation of origins is very simple. For any IR operation, we just select the origin of one of those of its arguments that has non-zero shadow. Since we work on a function basis, we need to propagate shadow through function calls. We use a TLS slot for that. So before, when we instrument a call instruction, we add all shadows for call arguments to this TLS slot, and this function, and in the function we extract it from the TLS slot and associate them with the argument temps. There is a big problem here with vararg. So when we look from the point of MemorySanitizer pass, when we look at VA arg, intrinsic, there is none. There is actually this huge piece of code, and somewhere near the end of it, the actual argument value appears. MemorySanitizer has a very hard time to figure out what is the shadow of this argument, because we only know shadows of the arguments as they appear on the call instruction. For that, we've got to make a terrible hack, which is platform dependent. We instrument VA start, and we prepare a piece of shadow that is in VA list format in such a way that all these codes, when instrumented normally with MemorySanitizer, will extract the correct shadow for this argument. It is obviously platform dependent. I'm pretty sure that we did not handle all cases completely correct, but it works for now. We haven't had any problem with that. Ideally, we would like front ends to not lower VA arg and just emit it as is, but apparently some backends cannot yet support this. Return instructions are instrumented the same way as calls. We've got another TLS slot. We push return value shadow to that, and then the caller can load it back. There are a lot of seamed intrinsics and other intrinsics that we also need to handle. We try to avoid listing all of them in our pass, so we just guess intrinsic behavior based on a modref behavior. There is a table for that, and intrinsic signature. We recognize several patterns like vector store and load, and general arithmetic intrinsics. these are kind of SIMD instructions that don't access memory, and for them we use the common propagation, which is bitwise OR of all arguments. And we have a special handling for memcpis, memmove, memset, varg, and bswap, which is very important because it's apparently very common to swap a fully initialized value with an uninitialized value. MSan is pretty fast compared to dynamic tools. It is, without origins, it has about 3x slowdown, and it uses twice as much RAM, simply because we have one-to-one shadow, and we don't have any red zones like AddressSanitizer, so it's exactly 2x. If we track origins, we add roughly another 2x CPU on top of that, because essentially that's another load, per application load, and store per application store. And we have another shadow, so that's 3x, and some memory for malloc stack traces to report origin locations. We did quite a bit of work on optimizing all that. The main point is MemorySanitizer must happen very early in the optimization order, because it inhibits inlining due to all this TLS magic, and because of that, it has to deal with a lot of optimizations that are done before, like that one, like this one, which happened in inst-combine, and this is not something that people do, but we have to deal with that because we run late. MemorySanitizer instrumentation is pretty complex. We write another program alongside the original one, so there is benefit in rerunning most of the normal optimizations once again after our pass, and we've seen it give us 13% performance improvement. This work is far from completion. There is more stuff that can be improved. For example, currently optimizers do not know that our application shadow on the origin memory never alias, and this leads to some suboptimal codes. And origin tracking is a thing that can happen lazily, mainly because most of the values that programs work with are initialized, and there is no sense in tracking origins for them. So it should be possible to do all the calculations, for example, in a basic block, and then if we notice that the result turns out to be poisoned, we can go back and find out the origin for that. Currently, code for origin tracking and for shadow tracking is kind of interleaved. Deployment of MSan is not that easy, mainly because MSan ideally needs to observe all instructions that are executed in a process. At the very least, it needs to observe all stores to memory, because some store that is not observed can turn an uninitialized memory location to an initialized one, and if we miss that, we will print a false report. We deal with that with a number of ways. First of all, it's pretty easy to compile lib C++ or libs to the C++ with MSan instrumentation and just link it with your program. For libc, which is much harder to recompile, we provide a large number of wrappers for libc functions. These wrappers mostly call the original function and then fix up the shadow so that it represents what happened in the library function with memory. We provide several handlers for raw system calls. They're currently not hooked anywhere, but there are several alternatives we think of. For example, in the future we could use something based on ptrace or on seccomp BPF infrastructure in Linux kernel to intercept system calls and call these handlers. They're only needed when an application does raw system calls. This way works when, so if it is if for an application it is possible to using all these methods to handle all the instructions, MSan is a very fast tool. It adds only about 3x slowdown, and for example we can do that for Clang. We've got a bot that continuously builds bootstraps Clang, runs all its tests, then builds another Clang with an instrumented copy, and it does find about 1 bug per month in Clang and LLVM. Currently, for infrastructure reasons, we cannot expose it to the public, but we do report bugs that come from it on the mailing lists. We've got another simple but slower solution. We've got a DynamoRio based tool that does some very simple instrumentation for the libraries that we were not able to instrument statically. This instrumentation simply declares all memory that is stored to in uninstrumented code as clean, fully initialized. This way we may lose some bugs if, for example, some uninit value is passed through the library and returns back initialized, but at least we get rid of false positives. As all dynamic instrumentation tools, it has especially slow startup, and even for long-running programs, it adds roughly 2x overhead CPU. But this is a way to get something running fast. For example, we were able to run entire Chrome browser on it, and remarkably, as Chrome is mostly I/O bound, we've seen roughly 30% slowdown, I think, on that. So it's even usable. So that's roughly what MSan is about. Questions?
Regarding the VAR lowering, I don't think that it's terribly viable to actually lower, but to actually have front-ends emit the VAR intrinsics. I think what would work a lot better is to teach the front end to emit your instrumentation for VARs.
Sorry, to emit what?
The VAR intrinsics aren't fully functional. They don't support the full ABI that languages require for VAR calls. And that's one of the reasons why Clang, for example, manually lowers them. And I think that's actually a good thing. And we need to just go and teach Clang to also introduce MSan instrumentation where it can, because it knows exactly where the variables are going.
Yes, I think it's possible. We could teach it to emit some kind of MSan intrinsic to at least mark the location where this argument value pops up.
Exactly. So the other thing, the question, we talked about using TLS to communicate the return value of poison state or shadow state and the argument shadow state across function call boundaries. Have you looked at instead changing the function signatures for internal functions and passing the state in as normal arguments and getting the state out?
We thought about that, but this changes function signature. And this may be trickier, especially if this function can be called from outside.
That's why I said internal functions. So LLVM marks functions which you're allowed to change the signature of as internal. And it would be useful to just do this
Yes, this may be helpful.
One of the other things that would be very useful is you can actually take every external function and convert it to a shim external function that reads and writes the TLS, and then immediately calls an internal function with the adjusted signature, so that every call within the translation unit doesn't use TLS. Just an idea.
Yeah.
How do I use it?
How do you use it? So there are two modes of use. The first one, if you can, if you have, for example, something like console program, the one that doesn't depend on too much external libraries like GTK, libx or something, and you are able to build all the code for that with Clang, then just do that. The option is called -f-sanitize equals memory, and there is another option that turns on origin tracking. It's called f-sanitize memory track origins, all with dashes, and then you just run it. That's all. If you cannot instrument all the code like this, you do the same for the code you can instrument, and then there is you find this MSan tool. The code isn't public, but you'll need build rules are kind of complicated, so you need to download this DynamoRio. The code for that is located in LLVM repository under compiler rt lib msander, and then you just prefix your program at runtime with this.
So what sort of operating system dependencies do you have in this, and are they as tangled in horrible, badly structured if-defs as they are for AddressSanitizer?
Currently we only support Linux 64-bit, x86 64. Most of our OS-dependent and RG-dependent code is shared between sanitizers. We've got a sanitizer common part that is pretty large. So if we decide at some point to port it to other architectures, I don't think we will get many new if-defs. Porting to other operating systems other than Linux might be trickier because we rely on libc interceptors a lot, and that's a lot of work to write them for different OS, and Windows is almost out of the question. Porting this tool to some other, like to 32-bit Linux or to ARM, might be not that hard.
So I'm interested in being able to enable this for FreeBSD because we build our entire tree with Clang, and so it would be trivial for us to compile FreeBSD, libc, libc++, everything that we ship with the base system with this for debugging. I haven't looked at the code for this. I looked at the code for AddressSanitizer, and there are a lot of ways you can structure code that make it easy to port to operating systems. AddressSanitizer was a case study in how not to write portable code. So I wondered if you had actually thought about splitting out the platform-dependent bits and the platform-independent bits.
We try to do it. We try to do it always, but sometimes it's still entangled.
I'd like to encourage people to submit patches to improve that situation if they don't like it.
Yeah, you mentioned that you kind of propagate the poison bits on arithmetic instructions. What instructions do you choose to actually report errors on?
Sorry, what instructions do I?
On what instructions do you report uninitialized errors on?
Currently, we do report. We do report unneat use by default for all instructions we do not handle. So at the beginning we used to report a lot. I think now we only report on some rare instructions that just did not cause problems for us, that we didn't notice. and we report on conditional branch, and we report on syscall argument and standard library for function argument in our interceptors. And as for IR instructions, that's conditional branch and maybe some rare instructions. We try to do this, we try to not report too much because it is simply slower. It's often slower than propagating.
So what's the issue with getting MSan to run on Windows?
It has very complicated API, so at least it has a very different API, so you'll need to write all the interceptors for the code that you cannot compile with Clang for standard libraries. And as far as I know, memory effects of some of those are not publicly known. They're not documented. Mm-hmm. It's the same problem that Valgrind faced when attempting to port to Windows. I'm not sure if they did it finally, but...
So it's a interceptor issue and not like a memory layout issue?
Yes. We've got AddressSanitizer kind of working on Windows, and from memory layout point of view, they are similar. So that's an environment issue.
Right.
You said that for libc you wrote some wrappers around the libraries that you didn't have to recompile libc. Is a user able to do the same kind of stuff for his own libraries that is not allowed to recompile? For example, a proprietary library or something like that?
There are some libraries for which we can do it realistically, and there are libraries for which we cannot.
But you say you say you can do it, but is a typical user of this tool, can he do it without changing the tool source code?
Yes, we provide interface for manual poisoning and unpoisoning of values. So, for example, I think we already use it in LLVM. Since a few days ago, LLVM depends on libz for some compressed debugging information stuff, and to preserve to allow this mode for Clang, we've had to add a few unpoisoned calls around calls to libz functions. So if the user knows what happens with memory in his program, in a library in his program, then yes, he can do it.
Any more questions? We have a few minutes left. Okay, so thanks a lot. So now it's coffee break time. Coffee will be served